Hi everyone, today I'd like to talk to you about some particle physics. My name is Andrew Connaboy. I'm a former student of Mr and Mrs Grant from Crieff High School. I'm soon to complete my master's degree in physics from Edinburgh University, and I just thought that during this time as school's off, probably the last thing you want to do is some physics, but just a quick 10-minute video talking to you a wee bit about particle physics and a wee bit about how we perform particle physics experiments, how we take the data, and what I'm doing. So getting straight into it, here we have the standard model of particle physics behind me, and with a little bit of knowledge of subatomic physics like the Bohr model of the atom, you'll be familiar with about 4 particles from this at least. So firstly, let's think about the hydrogen atom. So we have a proton as the nucleus orbited by an electron, and immediately you can tell here's the electron in the standard model, so that's the one particle there. And then the proton is divisible, so we can divide the proton up into its 3 constituent quarks, and these are the 6 quarks of the standard model here. The proton contains 2 of them, contains 2 up quarks and a down, so 3 quarks in the proton. And then in the neutron, in like other systems other than hydrogen, we'd have 2 downs and an up quark. So there we've already covered most of this first column here. The last particle of which is the electron neutrino. I won't say too much about neutrinos, except that they are extremely light, electrically neutral. There are billions and billions and billions of them going through every square centimetre of your body every second from the sun. So that's that first column dealt with, and I can quickly knock out the other 2 columns by telling you that they are exactly the same but heavier. So this column here is heavier than that, and this column here is heavier than the second column. And they're the 3 generations of matter. Now we can quickly move on to the bosons. So bosons are particles which propagate the fundamental forces. There's 4 fundamental forces, 3 of them are in the standard model. The strong nuclear force, the weak force, and electromagnetism. Gravity is not in the standard model, and that's one of the great problems of the standard model, is where does gravity fit in, how does it operate in the quantum level. So bosons propagate these forces. The 4th particle in the standard model you'll be familiar with is light. Here's the photon of light, the quantum of electromagnetic radiation, symbolised by the Greek letter gamma there. And then we have the strong nuclear force that's keeping lightly charged protons or quarks together in the nucleus. Together in the nucleus or together in the proton itself. And that is propagated by the gluon, massless gluon, keeping all these lightly charged particles together. The weak nuclear force, which is responsible for radioactive decay in the americium in your smoke detectors, in the uranium at Torness, the nuclear power station near Edinburgh, in nuclear bombs, or in the Trident submarines, for instance. And then lastly here we have the Higgs boson, which is extremely complicated. As an Edinburgh student, it's got very close ties to Edinburgh University. It's the theoretical work for the Higgs boson, a lot of which was done at Edinburgh by Higgs himself, so I'm lucky enough to sit near a framed Peter Higgs blackboard every day, which is quite an honour as a physicist. So I have 3 diagrams here showing decays from electromagnetism, weak and strong here. So don't worry too much about what is in these diagrams. Just nice to sort of give you a bit of understanding of how we can represent these phenomena. So starting on the left, we have the matter-antimatter annihilation of an electron and the anti-electron to give light. We have the weak decay, and this is a proton decaying weakly to a neutron. So proton, neutron, W minus boson, electron, anti-electron neutrino, and the strong decay. This Feynman diagram is from my master's project. So I'll hopefully talk to you a bit about that later on, but just now we'll just swiftly move on to the Large Hadron Collider. The Large Hadron Collider, the LHC, is one set of experiments that are carried on around the world to give data and see how well our models, our standard model, fit the data that we find. So the LHC is in Geneva at CERN, on the border between Switzerland and France. It's a 27-kilometre long circular collider on which there are 4 experiments. So what happens is that protons are accelerated through electric fields kept in circular trajectories using very strong magnets, accelerated up to 99.999999% speed of light, and then collided at these 4 points, which are ATLAS, CMS, ALICE and LHCb, the 4 experiments. My project work is done using LHCb data, and all these experiments are they're designed to find different things. So, show you a photo here. Of CMS. CMS happens to have some particularly beautiful photographs, which is why I'll show you these ones. So here you can see a scientist looking over his shoulder at CMS, and this is where the beamline's coming in, just across the page left to right here. So this enormous detector to find these processes going on at tiny length scales, mass scales, time scales, because we need to take in all the data we can. We need to really push the forefront of hardware and software alike to describe these processes and see how accurate our theoretical models are. And here's another photo of CMS looking straight down the beamline. It's some absolutely brilliant photography at the LHC as well, some absolutely amazing physics. So the CERN website has some amazing photographs. Even if you're not interested in the physics, just looking at the photographs is fantastic. So I'll move on to LHCb. So LHCb, the experiment itself is designed at looking at physics processes which involve quarks from the second or third generations of matter, so the heavier quarks. And so this here is Velo vertex locator. So the second and third generations of quarks they're very unstable. They exist for very small periods of time, which they decay back down to that first generation of matter in which we exist. So in order to capture these processes, LHCb's hardware has to stay very close to the beamline, otherwise all the processes are going to have happened before they actually get to the detector. So Velo gives really amazing resolution and accuracy on the mass of these particles. And different parts of the detector do great jobs of giving information about different parts of these different quantities of these particles. So, for instance, we have ring imaging Cherenkov detector. That part of that subdetector in LHCb does an amazing job of giving values of the momentum. So, by understanding the momentum of these particles, we can start to piece together what has happened at the collision point and working backwards, really reverse engineering what we see at the detector, reverse engineering back to what's happening at the proton-proton vertex. So, now I'll quickly show you sort of hadron structure. So one thing I look at is a hadron containing C quarks, charm quarks. So here's a hadron in the middle of this. We have the three quarks in the hadron, and what I look at is CSD is one thing that I look at, and how this hadron decays, and how the strong force, how the quantum chromodynamics on the quantum level, quantum chromodynamics describes the processes that hadrons like this undertake. So as I said, held in this hadron are gluons connecting these quarks. But it gets, unfortunately for us, it gets a lot more complicated than that, and we have quarks popping in and out of existence within this hadron, connected by gluons. So a sort of amazing fact that just doesn't make any sense is that only about 50% of the mass of a proton is contained by these three quarks. The rest is coming from these C quarks here and C gluons that are just popping in and out of existence and sort of making things really difficult for us. So when these protons collide at the LHC, a lot of what's happening is interactions between these C quarks as opposed to these valence quarks is what we call them. So by taking the data from LHCb and working backwards and developing an understanding of what's happening at the collision point, we can understand what's happening inside the structure of the hadron a lot better rather than just guessing. And unfortunately for us, there's still so much work to be done, as theoretical and experimental predictions are not lining up as well as we'd hope to in some very niche but key areas. The standard model is fantastically accurate almost all the time, except in some small locations. So by collecting more data and hitting more protons together, we can hopefully figure out what is going on the structure, on that level of structure. So that was just a quick talk to you about what my work is doing. It's a great passion of mine now, and even if that doesn't interest you, there's always some great photos to look at at CERN. Thanks very much for listening. Thanks.